today we want to consider electronic configuration. What is electronic configuration? It's simply the arrangement of electrons into their orbitals or shells. Well, there are three important rules which are necessary for arranging electrons into their shells or orbitals. The very first one is the Aufbau principle. The second is the Hund's rule of multiplicity. The third is the Pauli exclusion principle. So we're going to take all of these principles now. The first one, the Aufbau principle. It says that electrons occupy each orbital in order of their increasing energy level. You see, the order of increasing energy level is given below. So we have the 1x, we have the 2x and 2p. We have the 3x, 3p, and 3d. We have the 4x, 4p, 4d, and 4f. We have the 5x, 5p, 5d, 5f. We have the 6x, 6p, and 6d. We have the 7x and 7p. Not as though we must stop at 5f. Someone should say, if this one stop at 4f, why not 5f? And there should be a g, for instance. But we've not had reasons to use anything here, because all of this gives us the arrangement of any electron we have among the available elements. So as time goes on, probably they discover more electrons, then we might have reasons to feel beyond the F. But for now, we have the S, P, D, and F. Okay? So we have 1x, that's what Aufbau is telling us. This is the order of the increasing energy level now. For 1s, we move to the next one, 2x. Another filling the 2x, we move to 2p and then to 3x. After filling the 3x, we move to the 3p and 4x. After filling the 4x, we move to the 3d, 4p and 5x. Another filling the 5x, we move to 4d, 5p and 6x. Another filling the 6x, we move to 4f, 5d, 6p and 7x. And then we move to 5f, 6d, 7p. So that's that. So the order is like this. The very first one, 1x. The next one, 2x. The next after this is the 2p. After the 2p, we have the 3x. After the 3x, we have the 3p. After the 3p, we have the 4x. After the 4x, we have the 3d. After the 3d, we have the 4p. After the 4p, we have the 5x. After the 5x, we have the 4d. After the 4d, we have the 5p. After the 5p, we have 6x. And when we have 4f. After the 4f, we have 5d. After 5d, we have 6p. After 6p, we have 7x. And then 5f, 6d, 7p. So this is the order of increasing. So electrons moves from 1x. After the 1s is complete, it goes to fill the 2x. And so if I'm writing the electronic configuration of sodium, for instance, which is the 11th element, and I write 1s2, 2s2, 3s2, 2p6, 3x2, and 2p5. I'll be wrong. Why? I have not followed this order. Though I have used up the 11 electron sodium should have, but I have not followed this order. So this is wrong. I have not obeyed the Aufbau principle. Why? Because I must follow the order of increasing energy level. So that's that about the Aufbau principle. It's understand to take note that, you see, that p orbitals, or p sublevel actually, p sublevel takes 6 electrons, and then x firstly actually, s sublevel, or you can say s orbital takes 2 electrons. the D sublevel takes 10 electron and the F sublevel takes 14 electron. So that's that about the Aufbau's principle. So the next one is the Hund's rule of multiplicity. You see, it says that in any degenerate orbitals, electrons are filled singly first before pairing takes place. What this simply means is this. Look at the X, for instance, the S sublevel. The S sublevel has just one orbital. It doesn't have degenerate orbitals. But the P sublevel has 3 degenerate orbitals. Degenerate means that they have same energy. So these are P degenerate orbitals that make up the P sublevel. So understand the difference between orbitals and sublevel. These boxes are the orbitals. The whole of them like this is the sublevel. So all of this is the P sublevel. And the P sublevel has 3 degenerate orbitals. The first one is the Px, second is the Py, and the third is the Pz. Now, again, the D has 5 degenerate orbitals. The D has 5 degenerate orbitals. So these are the 5 degenerate orbitals in D. This is the D sublevel. So understand, the whole of these boxes make up the D sublevel. And each of these boxes make up the D orbital. And that's why if you are asked, how many electrons can the P orbital accept, take maximally? It is 2. But how many electrons can the P sublevel take? It is 6. Understand that. So don't say P orbital can take 6 electrons. No, it is the P sublevel that can take a maximum of 6 electrons. But the P orbital takes 2. The same goes for the D. The D orbital can take 2. So you now understand that any orbital can accept 2 electrons maximally. But the sublevel differs in the number of electrons they can accept. The F actually has 7 orbitals in it. So the F sublevel has 7 orbitals in it. So you can see 7 boxes. The boxes are what we used to represent the orbitals actually. So this is the F sublevel. It has 7 orbitals inside of it. Now when filling these orbitals, imagine I want to place 2 electrons here. I will place it 1, 1, not this way. Wrong. It's wrong to do like this. For instance, let's look at the electronic configuration of nitrogen. Nitrogen is the 7th element. And you know that should be going from 1x2 because S sublevel can take 2. Remember, from Aufbau principle to 2x2 and then to 2p3. 2, making the 4 you've used out of this 7, remaining 3. Placing the third one in the P. The P can take 6. Now, if we write this now, the any x, be it 1s, be it 2s, be it 10x, has just one orbital. So place electron here and place electron here. Place electron here and place electron here. But when you are filling this now, it is wrong to say that it's going to look like this. Very wrong. Why? Because you are filling a degenerate orbital and you must fill singly first. Singly first. So take note of that. So that's that about this. The right way to do this is to say 1, 1 and 1. Not putting 2 and 1. No. You fill singly first. So that's that about the Hund's rule of multiplicity. Let's take the last one, Pauli exclusion principle. And so it says that no 2 electrons can have the same 4 sets of quantum number. Okay? Well, because you've not done quantum number, or you don't have idea of quantum, you may not understand this. But if you understand quantum number, you understand this. So, but in our later class, we will look at the quantum number. You see, what this simply means is that, look at these two electrons here. They have 4 quantum numbers, which is the principal, which is represented with n. The n is what this one is showing us. And this one is telling us it is K shell. If it is 2, it is L. If it is 3, it is M. If it is 4, it is N. So that's K shell. So the n is 1, which is K shell. Now, it has L. The L is 0. Why is it 0? Because of this S. Is 0. Now, the next one is M. Now, the M is still 0. Because X, 0. Well, because you don't understand. But look at my points here. None of these are my points. Even though you don't understand it, there's no problem. But the most important thing here is this. As you look at these two electrons, their spin differs. One is pointing upward plus half. And the second one is pointing downward, which is minus half. And so you see that their spin differs. Even if their principal quantum number, azimuthal quantum number, and the magnetic quantum number has the same, their spin differs. If it is possible to write this thing like this, you'll be violating the Pauli exclusion principle, because all of they will have the same first set of quantum number. Their spin the same, their magnetic the same, their azimuth are the same, and the principal are the same. So the implication of Pauli exclusion principle is simply that if one electron in an orbital points upward, the other one will point downward, so they have different spin, because they cannot have the same first set of quantum number. If I put 2 electrons here like this, it will be wrong. Why? These 2 electrons in this orbital now have the same first set of quantum number, and we can bring that out. The principal is n, which is 2, which is talking about the L shell. So this electron here is in the L shell, and this electron here is also in the L shell. And again, if you ask for their L, because they are P, their L will be 1, which is the P sublevel. If you ask for their M, remember I told you that this is PX, PY, and PZ. This PX is represented with -1. So their M is -1. So why this is -1? This is also -1. The 2 electrons here are -1. But their spin now would be, if they are in the same direction, plus half and plus half, which will be wrong, because they have not have the same first set of quantum number. Hence, this should point like this. That's the implication of the Pauli exclusion principle. So that's that. We'll be showing electronic configuration for the first 30 elements here.
Let's look at the electronic configuration of the first 30 elements. Now, let's begin with hydrogen, which has just 1 electron. So this will be 1x. The 1x is the first one, 1. We are putting 1 electron in the 1x. And then we have 1x2. This has 3 electrons. The atomic number is 3 and it's neutral, so it has 3 electrons. This will be 1x2, because the x can take only 2. The remaining one, after 1x, move to 2x. So the 2x takes 1. You know, every x can take 2, and the p can take 6. They are sub-level, that's what we're using here. The d can take 10, f can take 14. Remember that. So this stands for put 2 in the 1x and put 2 in the 2x. So we utilize these 4 electrons that beryllium has. Both one has 1x2, then put 2 in the next one, 2x2, and then 1 is still remaining, but we just use 4. Then the 1 we fill in the next orbital or sublevel, which is 2p. So move from 1x to 2s, 2s to 2p, 2p to 3s, 3s to 3p, 3p to 4s, 4s to 3d. Remember from Aufbau principle. So this one carbon now, this will be 1x2, 2x2, then put 2 in the p. The p could take 6, so we are still going 1x2, 2x2, and 2p 3. The next one now 1x2, 2x2, and 2p 4. This will be 1x2, 2x2, and 2p 5. This will be 1x2, 2x2, and 2p 6. And this will be 1x2, 2x2, 2p6. The p is already filled, so we move to the next one, which is 3s. And remember, any s, be it 1s, 2s, 3s, 4s, can take just 2 electrons. So this s remains one to be filled, and beryllium fills it. That will 1x2, 2s2, 2p6, sorry, and then 3x2, that's okay, 13, which is 1x2, 2x2, 2p6, this x is filled, so we have one left because this is 13 and we've used just 12 here. So the one remaining, we move to the next one, that 3x, which is 3p1, so 1x2, 2x2, 2p6, 3x2, and 3p2. 1x2, 2x2, 2p6, 3x2, and 3p3. So we can do this on and on and on. You can continue on your own, but I'm going to complete this so you can see it. This is the complete for the first 30 elements. You can proceed for any element. The idea is just the same. We want to take the electronic configuration of the first 20 elements. This time around, we want to show the orbitals. And so let's begin now. The very first one, hydrogen, it has one electron. And so, one electron in the s orbital. Helium has 2. Lithium has 3, so 2 here, and then 1 here. Beryllium has 4, 2 here, and then 2 here. Boron has 5, 2 in the 1x, 2 in the 2x, and just 1 in the 1p. Carbon has 6, 2 in the 1x, 2 in the 2x, and 1 here. Nitrogen has 7, 2 in the 1x, 2 in the 2x, 1 in the 2p. And so for oxygen, it has 8 electrons. 1, and then 1 here. Remember, it will point down when you pay because of the Pauli exclusion principle. So this is. So you fill singly first before you start pairing. So when you finish any of that, you want to put 6 here and you put 1, then you start pairing. That's how it goes. So I guess you can do the rest. So this is how everything looks like for the first 20 elements. And then on and on, you can do for the 21st. You can do for the 21st, I'll start filling the 3p orbitals. So that's that, not 3p, sorry, 3d orbitals for the 21st. That's from scandium downward. But we want to stop for the first 20 elements. So that's that.